to today's webinar with the title Reliability Through Teamwork, Designing and Testing HDI PCBs for Harsh Environments. I am Andreas Schilp, your host of today's Würth Elektronik Circuit Board Technology webinar, and I would like to welcome you. The speaker in today's webinar is a qualified specialist from Würth Elektronik, Andreas Dreher, from our Technical Project Management. Welcome back, Andreas. And now I wish you lots of fun and new information.
Thank you for your kind introduction, and welcome also from my side to all listeners to this very important topic. So a quick introduction. In the last times I was very often here as a speaker in our webinars, so maybe you already know me. If you want to contact me afterwards with any additional questions or with new projects in this section, feel free to use the available contact information, and we are happy to find a good solution for you. In the today's topic, in the beginning, to get all the data together, the most difficult situation was to decide what topics to include, because about reliability you can make a talk the whole day, write books about it. There are already a lot of books written about it, so it was pretty difficult to choose very interesting topics to keep in the time limit in the given time frame for the webinar. So let's dive in with a quick overview. I thought, for example, voltage breakdown is a very important topic. We will discuss a lot about temperature and temperature cycles. We have some mechanical stress through vibration or through different components. We have some harsh environment gases with some bad contents in the air for the PCB, and of course humidity is always a very interesting topic. But before we dive into these topics, what is reliability and what is a good definition of reliability? And that's here in my summary box for every topic. And I pretty much like this definition. It's so good. Reliability describes the ability of a system or a component to function under stated conditions for a specific period of time. I can give you different numbers for reliability of your PCB, but can you give me the stated condition or the specific period which you need this product working? Very often that is very difficult to answer. And in white section, a lot of customers have industry applications. Do you really know what your end customer is doing with your board? Are they putting it in a nice media room like we are here in the webinar, or putting them close to a galvanic line in a production which have different conditions? So very often it's very hard to define the stated conditions and the specific time. To measure the reliability is, compared to that, often very easy. So let's dive into the topics, and I would like to start with a simple one and we get more complex as further we progress through the slides. Let's start with humidity. The PCBs are built with a composite material, so we start with glass fibers, coat them with resin, apply some copper, and then multilayer is more or less done. The copper and the glass fibers are pretty stable, but the epoxy will definitely absorb some moisture from the environment. And here is an extract of our great summary, Physics of Humidity. I put a link in this presentation because Andreas Schilp had already given a nice webinar and a good summary with a lot of slides of it to it. There you can get more information to that topic. But as a quick introduction, if you use a dry PCB, put them in an environment like 40 degrees Celsius and 92% relative humidity, You can see that after a few days already a lot of moisture gets absorbed by the material, and it will continue for a very long period until it finally stabilizes and gets more stable. The question already, and that is design dependent, is what is the critical level? How much moisture is okay for the PCB, and then it is too much. And that's definitely dependent on the layout. There's no simple black and white answer. It's always a little bit gray. In this extract, or in this physics of humidity paper, you will find also some ideas about drying, how to get rid of humidity from the PCBs. And again, a layout is here a very important factor. You can see here we have a section with only resin, no copper at all, with a little bit of copper, some copper, and full copper, for example, on a ground layer. And when you do some drying, here in this example it's 15 hours, you can see that in the only resin area, the humidity gets very fast in, but also it gets very fast out. And as more copper you have, copper is a good barrier for moisture. It's harder to get for the moisture in. It can creep in from the edges, for example. But again, also at drying, it's harder to get rid of the moisture, so it has to move to the edges. You can see here in this graph on the edge it's dry, and in the middle it's still very wet. That's great. Now Andreas gets some coffee. That's one not translated page. One extract also is the packaging of the boards. So if you have a standard packaging of a typical PCB, it's only the PE plastics, and this is no protection for moisture at all. It's a mechanical protection. If you put a glass of water on it, it gets rid of the water, but the moisture in the air can pass through this PE plastic very easily and can go in and out as it likes. If you really want a moisture protection barrier, then you have to use these aluminum coated bags, which are better and have a high moisture barrier that you're really protected. In general, boards have to be dried before use, before assembly. If you get them from us, they are not pre-dried. So in general, you have to do it before the assembly process. There are a lot of things to consider, and as I mentioned, we already put a nice webinar and a very big summary together. You can find the link either directly today on our homepage if you check for moisture of physics, or you find later the link in the slides directly to the landing page where you can deepen your knowledge in this topic. So printed circuit boards are sensitive to moisture, and it must be evaluated depending on the layout, because the layout, as we already learned, have a big impact to the moisture content. Another topic is harsh environments for the PCB. And in the discussions with a lot of customers, I often get the answer, oh, we are just doing simple electronics for industrial applications. We don't have very high sulfur contents or high chloride contents. But in the meantime, we are now getting close to the summer season. A lot of big towns have in the summer a lot of smog problems in the air. And in the meantime, in big towns, you have a very high fan gas concentration in the air. A few years ago, we used such concentration for accelerated testing, and you have them already in the town, in the air. So really this can be a problem everywhere in all applications. On the other hand, if you have a look on some industry lines, that is one of our etching lines in our facility. You can imagine we have a lot of sensors, a lot of gauges on it, or you see here a computer in front of it as a control unit. And of course we have a lot of chemicals and acids in these lines. So again, the electronic has to be protected. And in that case, the standard computer has a separate housing to avoid any chemicals through the air getting to the electronics and trying to destroy them. Let's have a closer look what can happen to the different final finishes. Here you can see some pictures from a nickel gold test board, the standard Enix surface. And here we have the before, pretty shiny, pretty nice gold. And after only a few days with some harsh environment products, you see this aging where you have some residues on the surface. This surface wouldn't solder at all, and if you use that as a contact surface, for example for a press button, it would also not work. So there definitely we have to avoid getting the nickel gold to such even standard industry or standard smog atmospheres in towns. If we have an additional look to chemical surfaces like immersion tin or immersion silver, we have often copper migration, and you can see here in this animation I have used some test structure, only 10 volts DC, and I have a drop of drinking tap water on it, and immediately that's really live. You see after seconds some migration will happen, create a short, and the structure will fail. Of course, a drop of water on electronics is pretty strong, but also humidity on the surface can such a thing over weeks or months and will fail in the structure. So here, a summary to it, we have different causes. We have corrosion with especially sulfur or chlorine products. We can have some oxidation before the assembly. That is a problem in storage. After assembly, typically it's not an issue anymore. Or we have this kind of copper migration. And again, if you have a combination with moisture, this will accelerate the aging and can cause pretty fast problems. What are possible solutions? You have to protect the electronic for these areas. They are not made to withstand it. So a coating can help, like a conformal coating, or you need a sealed housing. For example, the picture with the computer with a sealed housing that you don't get any crazy substances on the electronic. So definitely here, the point is soldering surfaces are not corrosive protection surfaces, even if it's nickel gold. Some mentions are gold is not corroding. Yeah, true. If you put some ancient artifacts from the pyramids 4,000 years ago, they are still shiny, they look great, but they are massive gold. On the PCBs, we have only 50 nanometers, so it's a very thin thickness of the gold, and it's by the standardization a porous surface, so the sulfur, for example, can penetrate the gold and oxidize or corrode the underneath laying metals. So definitely you have to protect the electronics against that. They are not protecting themselves. So another very important and hardly discussed topic is mechanical stress in printed boards. The PCB itself, I mentioned already, is a composite material with glass fibers, epoxy and copper. We have additional the solder joints with some tin alloys. We have components. Sometimes we have an interposer, like in this case the BGA. This is a different base material to the PCBs. It's often a very high TG. You have the silicium die, the chip itself, with the wire bondings afterwards, and here some molding compound with fillers. Or on the right hand side you have a similar BGA but with a metal lid, which is often a nickel alloy. Sometimes it has some copper areas as a standoff or as a heatsink. Copper has a very good heat conductivity. Again, some different FR5 material, for example, and the PCB. And with all this mix of these different materials, that can cause internal stresses, especially if you change the temperature. Let's have a closer look. Here we have a microsection. On top you have a BGA with a molding compound. The silicon die is not hit here, it will be deeper into the component. You have the solder joints, the BGA balls here, and underneath you have a standard multi-layer board with some micro vias, buried vias, and a lot of tracks. In that case, the customer had the problem, but on the left-hand side there was some stress, and if we have a closer look, this ball is actually this one. There is a crack underneath in the material, and really the whole copper pad, including some resin, are ripped off this PCB. Another ball with a micro via in pad. The micro via had withstood the stress and was bending the inner layer, and here you can also see a crack into the material, and in that case it was connected by a track, and the track got a break and was destroyed, and that was in that case the failure mode for this board. The problem here was a mismatch between the component, the soldering temperature, and the PCB itself. And when you have a top-down view, here we have a grid with all the BGA pins, and you can see most of the corner cracks on one side of the component were really cracked and broken. Some had some beginning stress, and in the other area was a pretty good one. So what was the issue? Again, according to your layout, according to the different materials, and here are some real measurements of coefficient of thermal expansion in X and Y. We will later see some other additional graphs in the Z, in the thickness direction. So we took a little sample, measure it, and heat it up from 40 degrees, for example, to 220 degrees, and we see the length change according to the temperature. Here is the TG at 150, so it will bend here, and the glass fibers will take the most stress. That's the A section with only resin and glass fibers, no copper. If you have a look on the B section with a little bit of copper, you see it's the bending is not so much. The PCB is a little bit stronger, not so moving. And if you have in the D section, it's pretty straight with a lot of copper. You get some stability and not a lot of change over the temperature. The pure copper, if you compare it, is very stable up to the high temperature. And as less deviation you have between the different materials, as less stress you have, as more reliable it will be. And if you include now all the materials inside the BGA, the mismatch should be as low as possible. What was the customer's solution here? We changed the position of the component from the edge of a board more to the middle of a board, added a little bit more copper on the ground planes, that we get more stability, less stress, and afterwards the whole section was green. So the layout will definitely influence the mechanical properties of a printed circuit board, and in general, more copper will strengthen the board. So here we come to a poll, and I would like to know what is your maximum operation temperature for your application, and I will hand over to Andreas that he can set up the table for voting.
Okay, so you now should see a blue screen with 5 answer possibilities. Please make your choice now. Afterwards we will see the result, and I'm looking forward to all the explanations from Andreas to this really interesting thing. So we have passed 50% participation. I will wait another few seconds. And we already had a German session this morning, but now in this session the answers are quite different compared to this morning in the German session. So I will now close the poll, and show the results. So we have 29% for 85 degrees C MOT. We have 39% for 105 degrees C MOT. Another 18% for 120 degrees C. Just 5% with 130 degrees C MOT and 8% 150 degrees C MOT. So that's interesting, and I'm looking forward to Andreas' explanations. Thanks for that.
Yeah, thank you. That's a very good impression of the field. And in the morning we had a little bit more even distribution. Really, the whole section was met. Here in this international presentation, it's the temperatures are a little bit lower, which is in general a good thing, and the boards will withstand them a lot. Because if you would put the PCBs in hot coals, like shown here on the pictures, you don't should do it in the field, or at least add a nice heatsink to the PCB that it can withstand. So what is the maximum operational temperature? And there are different definitions in different standards. Let's take the UL as the most referenced standard. And there you take the boards, put them in the oven, heat them up to different temperature, wait for some specific time, and afterwards 50% of the mechanical strength and the dielectric breakdown voltage. If you achieve a 50% value, it's a pass. So you have the numbers and it's still a pass, and that's really a point to think about it. Is this really enough for your application, and where a safety factor should definitely add it. So for example, this is a section.
There's a question from one of our participants. The question is, what temperature are you talking about? TA, Tin, TJ? So I would assume it's TA, so it's the ambient temperature. Is that right?
Yeah, that's a good question. And to be honest, to translate that to the UL standard, definitely it's a good point, because that's why I bring it up. Maximum operational temperature, for me as a PCB point of view, maximum means maximum. So hottest point in the field. But there are definitely different specifications, and yeah, I to be honest, I don't, I'm not aware about this T-in, TAs. But what we do is, we take the board, put them in the oven, heat them up, for example, 1000 hours at 125 or 150 or 160 degrees. And you can see in the as received state, it's a nice black forest green. And after some temperature exposure, you definitely see a degradation in color, but also in the properties. The plastics gets more brittle, the solder mask gets more brittle, and the factors will change. And that's some point to consider. And we have a pass, for example, for our solder mask at 160 degrees, but the UL standard had for a few years ago the maximum level at all, the highest level in a paperwork is possible was 130 degrees. A few years ago, they added a second or a higher value with 150 degrees, which now modern base materials and modern solder masks can be listed in VUL to this temperature. But as I mentioned, a few years ago, even a TG 200 material was listed as a MOT 130 material, because there was no higher class. And that's very often a big discussion, and that's why if this is so important for you and for your application, we have to talk about beforehand. What do you mean? How do we define maximum operational temperature? Is it the UL standard, which is a pretty simple test, Do you have some other ideas? Do you have some peak temperatures? Maybe a component has some internal temperature which is locally heating up the board. We have to talk about such things if this is still possible. One example, the dielectric strength of some materials. And here we have, for example, the setup, how to test it on a board. We have a kind of multimeter where you can set up, for example, 1000 volts. And you measure then the resistance on some layout features. In this cross-section, we see the solder mask very often. The edge is the thinnest part. So we will test here and have some typical values. And there is a typo. I have to correct this one. So I think it's 40,000 volts per mil. And for us Europeans, I translated it, and then here it's also a zero missing. That would be 50,000 kilovolts for 10 millimeters. But can we calculate it down? For example, a typical thickness will be maybe 5 microns, maybe 7 microns on the edge. Can we calculate it down to some value per micron? Yeah, you cannot scale it down freely. There is some limit. The same is true for dielectrics like FR4 prepreg. With one prepreg, there is a chance the IPC allows some residues inside the prepreg per some area, and it can be that this residue will lower your dielectric strength. So if you have really a high voltage application, you should always use two prepregs, because the chance that some inclusions are in both prepregs on the same place is close to zero. So that's where you can use the high numbers. But if you have only 60 microns, like in this one, again, you have to really carefully consider, can you calculate down these high numbers to some low value. So here really typical values cannot be scaled in a very small thickness area. Another thing, and now Andreas gets a second coffee. Another thing is if you look on a data sheet, yeah, the typical numbers on a data sheet, they are carefully measured in a lab area, but can you use these values directly for your field application? Let's have a look on this very often used comparative tracking index, or in short CTI value. For the CTI value, you have such a device, you have two electrodes, apply some voltage, add here with this device 50 drops of a dedicated chemical, and after 50 drops you measure the breakdown voltage, where you get a big flash, and here we can see some burnt debris, which is a nice picture from the Wikipedia page. Do you have in your application such a setup where you can have, for example, 400 volts as a breakdown voltage? I don't think so. And again, here only the raw material, the core is tested, and it's not a real PCB. So the data sheet value is true, but can this value one by one translated to your field application? Or another example is the flammability test. Here you use a very closely monitored flame, put them 10 seconds to a test strip, and after additional 10 seconds the flame should be extinguished by themselves. If you have that, then you get a V0 by UL, for example. But again, do you have such an application in your environment in the field? Is this the one-by-one conversion for you? You can very good compare material A against material B with such values. But can you use such values in your real-world application? So definitely the transferability of datasheet values should be closely checked, and you really have to think what values you use for your setup. So now a very big topic came about temperatures for PCBs. That's the most discussed topic for PCBs. And a quick look what is in the life of a PCB, what temperatures are affecting it. In our production, according to the complexity, we have 1 to 4 press cycles at 200 to 220 degrees maybe. In the solder oven, the curing of a solder mask is done 1 hour at 150 degrees. Later in the assembly process, you have typically 3 times 230, maybe 240 degrees. For testing, we use 6 times 260, but please only use it for testing, not for a real process. That would be too hot and will destroy the PCB pretty fast. And the field application, as we mentioned, very often it's hard to define what the board will really later see. So there are a lot of temperatures to consider. Typically, we test them in a 2-chamber oven where you have an oven on top and some freezer below there, and the boards will move up and down between these 2 chambers. That can be half an hour or an hour cycles, and the temperatures can be defined. You can use some online monitoring, add some cables to the coupons and measure them and get an idea about the quality. There is an IPC standard for this evaluation to measure the resistance of a board, and for the IPC it's very important you have some milliohms in that, or ohms in that case, before, and then you do some cycling and you measure it also at the end, and if it's the beginning and the end is the same, it's a clear pass. There we can very fast agree. On the other hand, if you have some change, here it was 0.5 before, afterwards it was higher, there is some critical number which we can define together, or there is some standard in the IPC, and then again, pretty clearly, it's a fail. But we are working in a real life. What if with such a measurement? IPC check, before, after, the same, just with standard IPC, that's a pass. To be honest, I want not to fly with this kind of plane into the holidays. We have to check what happened here, and that can be very tedious and very time-consuming to find the problem here and to fix it afterwards. That was the thing. We have still the oven in use, but it was very hard for us in a qualification process to really understand what's going on. So we changed the test method to this Interconnect stress test 10 years ago already. So what is Interconnect stress test, or IST in short? We have different test chambers where we can add the coupons. We will add some cables, heat them with some currents, 7 to 10 amps, up to different values. In this graph it's 150 degrees for 3 minutes of heating and 2 minutes of cooling, only at room temperature. During this whole thing, we measure the resistance online, really live. We see the live measurement, and when the resistance change, for example 10%, that's defined as a failure. The test will stop. This single coupons, the others can progress. I can take this coupon, investigate and learn about what was happening to him. Let's have a closer look. We have different structures here internally. The golden one is the power structure, where we can add some current and heat the coupon up. And with a sense coupon we can measure different structures. For example, here it's a generic coupon where we test some small vias, some through-hole components, or that one is a more complex one, which was created for customer use with a complex HDI board with a lot of micro vias and through-holes, buried vias, where we can test individually, is the micro via more reliable, is the buried via more reliable, or what's the critical point. So you can really create individual coupons, and very often that's necessary and very helpful to compare different sections. In the following slides, we will compare different tests with the so-called viable evaluation method, and I don't want to go too deep into the statistical things. So in the graphs, for us very important is this 63.2% failure mode. That's for an viable evaluation an average to compare the average failure rate. The shape is not so important for our kinds of elevation. So here are some tests with mechanical vias. It's always the same board, nothing changed. They are produced in one batch, and we applied different test temperatures. The black line was 150 degrees test temperature, the red 170, and the green one was 190. And you can see for 150 degrees had a typical failure rate of 1,500 cycles when most of the coupons failed, which is pretty good. And of course, as higher you go in the temperature, as lower will the average cycles be. So after 400 cycles, most of 160 degrees coupons failed. And after only 120 cycles, 190 degrees failed. So if you have such a peak application, you can see the stress is pretty hard, and the factor between is very hard. So if you have some local peak temperature, that can destroy especially through holes pretty fast. Compare this to microvias. The microvias have a benefit. They are only connecting one layer to another layer, so the set thickness is pretty thin, so the stress is also thin. Here you can see microvias with different temperatures, and the temperature change over 1,000 cycles. It changed only a few percent. 10% would be the failure mode, so the microvias after 1,000 cycles didn't show any sign of wear and tear. So microvias through the low set value are pretty stable and pretty reliable. The same thing applies here. We compared here different thicknesses of a board. So we had a board, the target thickness was 2 millimeters, and for the test we added on some other boards with the same layout 2 prepregs to increase it by 0.2 millimeters, and we removed 2 prepregs to have a thickness of 1.8 millimeters. The 1.8 millimeter board had in the green section an average failure rate of 180 cycles. The 2 millimeter board had roughly 80 cycles, and the thickest one, the 2.2 millimeters, failed at roughly 60 cycles. So with this 20% of change of the thickness, you have a factor 3 in the reliability. So that's an important thing to remember. Every millimeter in thickness will directly affect the reliability. And again, a very hard comparison, if you create a very thin board with microvias and a small buried via, 0.6 millimeter thickness, we stopped the test after 2,000 cycles without any failure. They were still good and did not fail. We just had not more time to progress the test. So as thinner the board, as more reliable it will be. Very often I get in the last weeks and months the question, what is it about non-functional pads and what is our recommendation? We had a student which have done studies work, and he had to compare a lot of literature, and we really had a 50-50. Half of the literature told you should add the non-functional pads, it improves the reliability, and the other half of the literature said remove them, it will add more reliability. So that's why we want to do the test. We have the same board, produced them in one batch. Half of the coupons, the pads were removed. On the other half, the pads were included, and we compared small vias with 0.3 and bigger vias with 0.7. And here is the summary. Very interestingly, the small vias, of course, you have less copper, so they will generally fail earlier, but the 0.3 millimeters with non-functional pads failed pretty early with an average number of 150. And on the other hand, the 0.7 millimeter holes failed or had the best reliability in that test at an average of 290, so roughly double it. And the boards without, they had somewhere in the middle around 300. So that's very unfortunate. So what do we learn from this section? It definitely depends. Sometimes it's better to have them, sometimes it's better to remove them. So it definitely depends on the stack up, on your layout and on your board. So I think the literature is here pretty right, because they compare different layouts and you get always a different answer. So if you want to have a conclusive answer for your board, we are happy to offer you a test and test your design and get you some reliability numbers for your dedicated layout. What we also do internally, because the layout, as we learned now, has a lot of influence to all these tests, we want to know how stable are our processes. So we do a lot of process inspections with this test method, and we test more than 6,000 coupons in our Würth Elektronik facilities. We have in total 4 dedicated machines on different facilities to test our processes, always with the same layout. When you can see here the numbers from 2002 to the now completed 2003, and the reliability really was not moving very strongly, and we have here stable processes. On the right hand side, by the way, that's a typical picture if you visit our chemical lab in the morning. That's all the different samples from the different BEVs with the different chemicals, where they test a lot of different values for also the process inspection. So for us internally, it's a very important tool for process inspection, that we know our material, our processes, our machines are always the same quality. So let's sum up all these points. The test temperature must be carefully chosen. If you have a too high temperature where you just will burn and destroy the boards, the values are useless. If you are too low, you have to test for ages. It take too much time, and everybody knows time is money. You can design test parameters, for example, the PCB thickness. In general, as less thick the board is, as more reliable it will be. With non-functional pads, unfortunately, I have to tell you, it depends, but we are happy to offer you an IST test for your dedicated board and test it. Also, other tests, comparable tests. You can compare material A against material B, or if you want to test our competitors, feel free to order some IST tests from them, and we compare them on our machine and look who has more reliable boards. We use it internally for process testing, that we know our processes are stable, and also for very critical applications like avionics or nuclear power plants. It can be useful and healthy to test on a lot based before delivery, that everybody is sure the boards will meet the reliability you expect. Yeah, that was a quick walkthrough through a lot of different reliability points. I hope I met your interest.